Hello everyone, this is Daphne from CSM A section with pairing roll number 2340183357, and the subject is machine learning, and my topic is about Euclidean distance, most common and best for continuous data. And this is the topic. Introduction to Euclidean distance. Euclidean distance is a measure of the straight line distance between two points in a multi-dimensional space. It is commonly used in various fields, including mathematics, computer science, and data analysis. Understanding Euclidean distance is essential for analyzing continuous data effectively. Definition of Euclidean distance. The Euclidean distance between two points or p of x minus 1 comma y minus 1 and q of x minus 2 comma y minus 2 is calculated using the formula of square root of x minus 2 minus x minus 1 into 2 plus y minus 2 minus y minus 1 into 2. In higher dimensions, the formula extends to square root of sum I is equals to 1 into n into x minus I minus y minus I into 2. For points in n-dimensional space, this formula reflects the Pythagoras theorem, emphasizing the geometric interpretation of distance. And here we can see the formula d is equals to root x square minus x2 minus x1 whole square plus y2 minus y1 whole square is equals to root minus 1 minus 0 whole square plus minus 4 minus 2 whole square. Here we took the numbers of 1, 0, 4, 2 is equals to root minus 1 whole square plus minus 6 whole square is equals to root 1 plus 36 is equals to root 37. So the length of the line segment AB is root 37. Characteristics of Euclidean distance. Euclidean distance is sensitive to the magnitude of data points, meaning larger values can disproportionately affect the distance. It satisfies properties such as non-negative identity, symmetry, and the triangle inequality. The distance metric is most effective when dealing with continuous data, ensuring meaningful comparisons. And here we can see the Manhattan and Euclidean distances of the diagrams here. Applications of Euclidean distance. In machine learning, Euclidean distance often used in clustering algorithms such as k-means. It is also utilized in recommendation systems to find similar items based on user preferences. Additionally, it is a fundamental metric in page processing for comparing pixel values. Here we can see the two groups, and we can see here we can calculate the which point is nearer to the which group. Through that, we can declare that the point is considered to that particular group. Advantages of Euclidean distance. One of the key advantages is its simplicity and ease of interpretation, making it accessible for many applications. It is computationally effective, particularly in low-dimensional space, which speed up processing time. Euclidean distance provides a straightforward way to access similarities, making it a popular choice in data analysis. Here you can see the Euclidean distance formula. By using this formula, d is equals to root x2 minus x1 whole square plus y2 minus y1 whole square. Here I already heard that formula, and here you can see the graph about the Euclidean distance formula. Here we plotted the x-axis and y-axis, and a at the a point x1 comma y1, at the b point x2 comma y2. Limitations of Euclidean distance. One limitation is its sensitivity to outliers, which can skew results and lead to misleading interpretations. It assumes that all features contribute equally to the distance, which may not hold true in all datasets. Euclidean distance is less effective in high-dimensional space due to the curse of dimensionality. And here you can see the Euclidean and Manhattan's diagrams. Here in Euclidean, we can see the center and outlier windows, and here the same in Manhattan also you can see center and outlier window, but the shape of the object is totally different. In Euclidean, it is a circular, and in Manhattan, it is a spherical. Comparison with other distance metrics. Unlike Manhattan distance, which sums the absolute differences, Euclidean distance measures the direct line between points. Cosine similarity, another alternative, measures the angle between vectors rather than the distance, making it suitable for different scenarios. Choosing the appropriate distance metric depends on the specific characteristics of the dataset and the analysis objectives. Where visual representation of Euclidean distance. Graphically, Euclidean distance can be represented by drawing a straight line between 2 points in a two-dimensional space. This visual representation helps in understanding the concept of distance in relation to the coordinate axis. Such visualizations are crucial in educational settings to aid comprehension of geometric concepts. Best practice in using Euclidean distance. Normalize data before calculating Euclidean distance to ensure that all features contribute equally. Consider the context of the data and whether Euclidean distance aligns with the underlying relationships. Experiment with the different distance metrics when analyzing complex data sets to find the most suitable one. You can see the figure about that best practice for the Euclidean distance. Conclusion. Euclidean distance remains one of the most common and versatile metrics for measuring distance in continuous data. It, it is easy of use and geometric interpretation make it an indispensable tool in data analysis. By understanding its strengths and limitations, practitioners can apply it effectively in various fields. And here you can see the another graph about that. Here D is the hypothesis and x1 comma y1 and x2 comma y2. Here y2 minus y1 and x2 minus x1. Thank you so much for this opportunity and thank you so much for listening.